All right, hello everybody, welcome back to another video. In this video, we're going to be taking a look at a question from the IB Chemistry paper 2HL from May 2018. And this question has to do with acids and bases. And this is another topic which I see many students finding difficult, and even I found it quite difficult at one point in time. So this question is asking us to determine the pH of 0.01 mole dm cubed. So this is the concentration of an acid solution. So this is the acid solution, and this is its concentration. And they have given us the Ka value. So just off the bat, by the fact that there is a Ka value, you can tell that this is a weak acid because we use Ka to measure the strength of weak acids. And why that is, I have explained in a previous video. And if you want to know that in more detail, please go and watch my previous video. I'll put a link to it below and I explain it in detail. In this video, I'm going to be focusing strictly on how to calculate pH from Ka. So let's get into it. Now, what is the general formula of Ka? And Ka is the acid dissociation constant. So I'm sure you have seen Kc, you have seen Kb. Kb is for the base dissociation constant. This is the equilibrium constant. This is for equilibrium, this is for bases, and Ka is for acids. So this is the dissociation constants, right? Now, each of these have their individual formulas, but largely the formula is the same. It's the same. It involves us using the concentrations of particular substances in the reaction to calculate the value. So, for example, if you're familiar with Kc, you know that the formula for Kc is the concentration of. So I'm going to put concentration conc. I'm going to abbreviate it. So concentration of product one, and then it's raised to the power of its molar ratio, and then it's the concentration of product 2 if there is a product 2, and then it's times, and then it's divided by the concentration of reactant 1, and they're all raised to the power of their respective molar masses, and then this is times the concentration of reactant 2 if there is a reactant 2. This is the formula for Kc, and Ka is the exact same thing. However, Ka is slightly more simpler. It's the exact same thing, the exact same process, but it's simpler. And I'll show you why it is simpler. Let's take a look at the formula for Ka. So I'm going to have an imaginary acid. This imaginary acid is called Ha. Now, H in this is for hydrogen. All acids contain hydrogen, or at least the acids that we deal with in this do contain hydrogen. So when this is a weak acid, Ha, when it dissociates, it forms H plus A minus, right? That's what an acid forms when it dissociates. So for example, if I'm dealing with something like ethanoic acid, which is a very common type of acid, you see it coming up all the time in exam papers, and it's also used in vinegar. So when ethanoic acid, when you put it in water, it dissociates, it breaks apart. So what does it dissociate into? It dissociates into CH3CO minus, which is the ethanoate ion. And of course, it gives off one H plus. So this is the dissociation of ethanoic acid. The same thing can be applied for other acids, for other weak acids like methanoic acid. If you have methanoic acid, for example, it's CH3OOH. So it looks, this is methanoic acid. And when this dissociates, it's the exact same thing. You just remove one hydrogen, so it forms CH3CO minus plus H. Oops, sorry, I made a mistake. CH3OO minus plus H plus. So as you can see, there's a very common pattern. One hydrogen is removed and the rest is given a negative charge, or it's become an ion. So this is basically the dissociation. So when you have to calculate Ka, if I'm supposing I need to calculate the Ka for this reaction that I have just written over here, I'm going to ignore these for now. So if I want to calculate the Ka of this, it would be the concentration of H plus times the concentration of the ethanoate ion, the ion, A minus the ion, divided by the concentration of the acid. That's it. That is the formula for Ka. It's the exact same thing as the Kc formula, But however, one small change over here is that we don't really have the numbers on top, because for most part, the molar ratios in acid dissociations remain 1 to 1 to 1. So you don't have any numbers that you need to square these concentrations to, right? So all we have to now do is substitute the values that we know from the question into this, and then do a bit of rearranging, and we can solve our problem. So we know the value of Ka that's given to us in the question, right? The Ka value is 9.333 times 10 to the negative 6. That's 9.333 times 10 to the negative 6, right? And they've asked us to calculate the pH. Now, the only way we can calculate the pH is if we know the concentration of hydrogen, or sorry, H plus. If we don't know the concentration of H plus, we can't calculate the pH, because pH literally stands for power of hydrogen. That's literally what it stands for, power of hydrogen. So we need to know what the concentration of H plus is in order to calculate the pH. And I'm sure you have done this earlier as well. For other acids like HCl, you often do negative log of the concentration of H plus, right, to calculate the pH. And the exact same thing needs to be done over here. We need to first get what H plus is. What is the concentration of H plus? And then we can do this step, which will give us the pH, right? Hopefully that makes sense to you. So we don't know. They have not given us what the concentration of H plus is, but they have given us the concentration of the acid. They've told us that the acid is has a concentration of 0.01. So the concentration, this is the number below, is 0.01. Because remember, the number below deals with the concentration of the acid. So what is the next step? Now, one thing that we can assume from this is that the concentration of both products is exactly the same, because how much ever H plus you produce, or how much ever H plus is dissociated, the same amount of ion will also be produced, right? So the concentration of H plus given and concentration of the ion formed is going to be identical, right? Because if you have HA and it breaks apart, it's going to give you the exact same amount of H plus, and it's going to give you the exact same amount of the ion that is left over. And let me give you a small analogy if you're having difficulty understanding this. Imagine I have given you two burgers, okay? And the burger contains two buns and a patty. So this is the patty and this is the bun, okay? These two on top of the bun. And if I break apart this burger, if I dissect it into its constituent parts, I'm going to get two buns plus one patty. And that is going to be true for any burger, right? Because one burger is only made up of these three things. Similarly, in the acid is made up of the hydrogen, or the H plus, and then it is made up of the stem, or the other things, or the ion. So when we break apart an acid, or when it dissociates, it's going to give us hydrogen, H plus, and the ion, and they both are going to be in the similar ratio to each other, 1 to 1. In the case of the burger, of course, it's 2 to 1, because we have two buns and one patty, but that's not the case over here. This is just a silly analogy that I made up over here. But hopefully you get what I'm talking about. So the concentration of H plus and the concentration of the ion is going to be exactly the same. That's why you can actually technically write this as H plus squared, because the concentration, remember, we're not dealing with the identity of the substance. We're just dealing with the concentration over here. So we can technically write this as H plus squared, because the concentration of H plus A is exactly the same thing. So suppose the concentration of H plus is 2 and the concentration of A is also 2, you can just write 2 squared, right? It's the exact same thing. So similarly, we can just write it as H plus to the power of 2, because the concentration of H plus and A minus is the exact same thing. So in relation to our question, we can also do the exact same thing, because when 2,2-dimethyl propanoic acid will dissociate, when it dissociates, it's going to again give us the same concentration of H plus and the same concentration of the ion. I'm not sure what ion is exactly formed because I haven't written out the formula, but it's going to give us the exact same concentration. So now all we have to do is rearrange this equation, and then we will find out what the concentration of H plus is. So we multiply this side by 0.01, so this cancels out, and we multiply this side by 0.01, because whatever you do to one side, you have to also do to the other side. So then this leaves us with an answer of 9.333 times 10 to the negative 8 is equal to H plus squared. Now I want to remove the squared. I only want to find the concentration of H plus. So I have to square root both sides. And that gives us an answer that tells us that the concentration of H plus is, just give me a second, it is 3.0549 times 10 to the negative 4. That is the concentration of H plus. Now it's easy pickings for us. It's very easy. Now, if we want to calculate the pH, we just have to take negative log of H plus, so negative log of this number over here. If you just put that into your calculator, you'll get your answer as roughly 3.515. So that is the pH of 0.01 mole dm cubed of 2,2-dimethyl propanoic acid solution. So it's 3.515. That is it. That's it for this question. It is worth 2 marks. So that's fair amount of marks, and it does require a few steps, and mostly it is just math. So after you understand the concept, and hopefully you have, it's just math. You don't have to really do anything else. But please, when you do solve this question, show all your workings in the box. It shows the examiner that you understand what you're doing. Thank you so much for watching this. If you have any other questions regarding this concept or any other concept, please feel free to message me on my social media or send me an email or put it in the comments, and I'll be more than happy to help you. Thank you for watching. Take care of yourselves.